Good day, good people. Let us look at this activity here. Okay, let's analyze what's given there. A brass rod with a diameter 25 is enclosed in a steel pipe. We are given a diameter. We are given a brass rod. Okay, let's make it. Let's make it a bit thick. This is your brass rod. Okay. Even if you can write it with a black, yeah. Then it is enclosed. It is enclosed with what? With steel pipe. It is enclosed with what? With steel pipe. It is enclosed with what? With steel pipe. This part is a solid part. Okay. Then the pipe part of it, it is hollow. That's the diameter of the pipe, it is given as 50 mil, and we are given the thickness. We are given the thickness of the pipe. It means you are even something like this. The thickness, that thickness, it is given as the thickness of that steel pipe. It is 10 mil. Okay. The diameter of the solid, it is 25 mil. Okay. Then we are told that it is rigidly fixed. It is rigidly fixed. Okay. Then the length of this pipe, it is 1 meter. The length, it is 1 meter. Okay. Calculate the stress in two materials. They want us to calculate the stresses in two materials when the temperature is increased by. Now, whenever you see this word increase by, you need to understand that that which it's given, it is the change in temperature. Right. How do we calculate the change in temperature? It is T2 minus T1. Okay. Now, how do we calculate the change in length as a result of the transference of energy or as a result of heat? It is the change in length equals to LO, coefficient of linear expansion multiplied by the change in temperature. Okay. Don't forget that formula. Just don't forget that formula. Also determine the resultant stresses. In the compounded bar, they want us to calculate the stresses as a result of heat, and then they want us to calculate the resultant stresses. They want us to calculate the resultant stresses. In calculating the resultant stresses, they want us to calculate the resultant stresses. That's what they want us to calculate. Stresses as a result of change of transference, that's what we need to calculate. Okay. Now, what else it is given here? We are given the axial load as 50 kilonewtons. Then we are given the Young modulus of steel as 200 gigapascal. Young modulus of copper, it is given as 100 gigapascal. We are given the coefficient of steel. It is 12 times 10 negative 6 degrees Celsius per degree Celsius, and the coefficient of copper, it is 19 times 10. Now, this is what we are given. Now, the first question, they want us to calculate the stresses as a result of heat. Calculate the stresses in two materials when the temperature is increased. Now, that is the first thing. Now, in calculating the stresses as a result of heat, now the fact that this is a parallel connection, let's write the principles that we know as of parallel connection. We know that change in length 1 equals to change in length 2. Length 1 equals to length 2. We know that force total equals to force 1 plus force 2. That we know when we are dealing with what? With parallel connection. We know that if we are calculating uh, the stresses as a result of heat under parallel connection, we are having force, open bracket, equals to 1 over area 1 Young modulus 1 plus 1 over area 2 Young modulus 2 close bracket equals to change in temperature open bracket coefficient 2 minus coefficient 1. Okay, coefficient 2 minus coefficient 1 or vice versa, coefficient 1 minus coefficient 2. Okay, that's what we have there. All right, now in calculating the stresses as a result of, we then have to calculate force from this formula. Area steel, Young modulus steel plus 1 over area copper, Young modulus copper equals to change in temperature, coefficient copper minus coefficient steel. We have to first calculate the force, then calculate the stresses. Now, in calculating the stresses as a result of the change or the transference of heat, we need this because we know that it will be stress steel equals to force over area steel and force over area copper. But this force, it is this force here that we need to use as a result of what? Of transference of what? Of heat. Now, that's the first thing that we need to do. But before we go there, we first have to then calculate the areas, the area of a steel pipe and the area of a copper. Now, how are we then going to calculate them? Let's erase so as to be able to calculate. Let's erase and be able to calculate. I will advance in technology. I would just advance and use the quicker slides in doing that. All right. Now, in calculating the area, let's look at the area of a solid bar first. That would be the area copper. It will be pi d squared divided by 4. Then we are having pi multiplied by our d. It is 0.025 squared divided by 4. Then we get our area as 4.909 times 10 to the power negative 4m squared. That's what I got in calculating my area copper. Then my area steel would be pi, since well the steel it is hollow, it will be d squared minus small d divided by what? By 4. Now we then need to get the small d. In getting the small d, it will be, remember the big diameter, it is given as 50. Then we are having the thickness it is given as 10. Now it will be the thickness on top of your steel pipe and the thickness at the bottom. That means it will be 10 plus 10, then we get 20. Then it will be minus, then when we minus 20 from 50, then we get 30. This would be the inner diameter of your steel pipe. Now we've managed to calculate the smallest diameter, the inner diameter, then we can calculate the area. It is pi 0.05 squared minus 0.03 squared, close bracket, divide by 4. Then I get my area as 1,257 times 10 to the power negative 6m squared. That's what I got as my area. Now we've managed to calculate the areas, then we can come in this formula and solve and calculate our F. Okay. Now in calculating the F, we are having F 1 over our area Steel, it is 1,257 times 10 to the power negative 6. Multiply by the Young modulus steel, it is given. Young modulus steel, there it is. Young modulus steel, it is given as 200. Okay, it is given as 200. It will be multiplied by 200 times 10 to the power 9 plus 1 over area copper. It is 4,909 times 10 to the power negative 4 multiplied by 100 times 10 to the power 9 close bracket equals to the change in temperature. It is 100 open bracket. The coefficient, it will be 19 minus 12 close bracket times 10 to the power negative 6. Okay, that's what we will have there as our formula. Then it is F open bracket. When we punch this value, the first value 1 over né, area multiplied by Young modulus, I get my answer as 3,977 times 10 to the power negative 9 plus this side I get my answer as 2,03707 times 10 to the power negative 8 close bracket. Then this side I get my answer as I punch 100. 19 minus 12 times 10 to the power negative 6 multiplied by 7, I get my answer as 7 times 10 to the power negative 4. Okay, now when we remove the bracket, we obviously have to add. When we add that, I get force close bracket equals to 2,43547 times 10 to the power 8. I used a lot of digits in dealing with that. 7 times 10 to the power 4. Then my F would be 7 times 10 to the power negative 4 divided by 2,43547 times 10 to the power negative 8. Then I get my force as 28,741,886 Newton. Then I can use this force to calculate the stresses as a result of what? Of the change in temperature. Now in calculating the stress, steel would be force over area copper. Then in calculating the stress steel, it will be force over area steel. Which force are we going to use? The force that we have calculated. It is 28,741,886 divided by area copper. Our area copper, it is 4,909 times 10 to the power negative 4. Then I get my stress there as 58,549 megapascal. Then my stress here, it will be 28,741,886 divided by area steel. Our area steel, it is 1,257 times 10 to the power negative 3. Then my answer would be not negative 6. My area, it is not negative 6 but negative 3. I've made an error in that. It is negative 3. Then I get my answer as 22,863 megapascal. Please, here I've made an error on area. Area, it is negative 3, not negative 6. Maybe some of you are wondering. We are using 6, but we are not getting that. It's an error from my side. It is 3, negative 3. Okay, the area here, it is negative 3, not negative 6. It is negative 3, not negative 6. Okay, please. It is negative 3, not negative 6. Okay, negative 3, not negative 6. Why is it? Negative 3, not negative 6. Okay, please rectify that as well. Okay, this is the stress that I got. Right. Now, we then have to determine the direction of these stresses. Okay. Now, let me I give you the simplest understanding on determining the direction. If this is the tensile and if this is the compressive. Now, you are having a hard material and a soft material. In this case, this is hard, this is soft. If these two are exposed to heat, you will realize that the weaker material, the soft material, in this case it is copper, it will extend quicker, it will respond quicker to the applied force, to the transference of energy. Steel, this is your steel. Because of it is hard material, it will respond slower, and still it will be the benchmark. Because of it is of hard material, it will be the benchmark for what? For extension. It will be the benchmark for what? For the change in length. If this is where steel ends in changing the length, you would realize then this is the benchmark. This is where the change needs to take place and needs to end. But check, as it's heading towards that benchmark, the direction there it is what? It is tensile. What is tensile? It is the force that pulls away from the material, from the object. Now you can tell that there's a stretch that takes place. It moves away from the object itself. Now, the stress here under steel, it is the stress tensile. But look at copper. Copper, it has extended beyond. But because of it has to be on that benchmark. Because on parallel, we said change in length on one material equals to change in length on the other material. It then means copper has to go back to that benchmark, to that level of what? Of steel. Now, if copper it is going back to that level, now what is this direction? You can tell that this is compression. It's the force that converges or that it is heading towards the material. Now it means the copper here under the change of temperature will experience what? Compression. It means here the direction of this it is stress tensile. Then here it is stress compression. We've then determined the magnitude and the direction. Compressive, the magnitude and direction tensile. Please bear in mind what we got as our stresses and their direction. Then let's go to the resultant stresses. For us to be able to calculate the resultant stresses, we then have to determine the stresses as a result of the applied force. We then need to determine the stresses as a result of what? Of the applied force. Now, you are having parallel connection. You are having the force total. That tensile force, axial tensile, it is the force total applied on this material. This is copper, this is steel. Now, check this. We then have to calculate the force that would be absorbed by copper and the force that would be absorbed by steel from that 50. We are having the total force of 50 applied on this material. But how copper going to absorb the 50? It's not the same as how steel will absorb that 50. Why? This one, it is of weaker material. That one, it is of hard material. Now, if you were to draw your stress and strain graph, in giving you a bit of understanding regarding that. Now, you are having the stress and strain graph. Stress, strain, or load and change. Now, there's a force of 50 kilonewton applied on this material. This is what you would realize. We are applying 50. As we apply 50, 50, then we realize that when we are somewhere on 20 kilonewton, then copper starts to deform. It means copper was strong from 0.220. Then it started to to deform. Then under that same force, when we apply that 50 kilonewton, then we realize that after 40 or after 30 kilonewton, steel starts to to deform. Steel starts to deform. Right. Now you can tell that from the 50 that we have, copper absorbed 20. What it is left, it is what? Copper absorbed what? 30. What it is left, it is what? It is 30. It then means steel started to deform after they've applied 30 kilonewton on that material. Then we will then have to calculate the stresses. For copper, we will calculate the stress from 20, and for steel, we will calculate stress from that 30. Now, that's what we need to determine. We need to determine the force that it is being absorbed by copper and the force that it is being absorbed by steel. From what? From this 50. That's what we need to determine. Now, another thing, if the force is being applied on this material, the change in length, it's a parallel. Change in length in one material equals to change in length in the second material. Now, the direction here, it is one way because we are applying the pulling force. We are applying the tensile force. We are applying the force that moves away from the material. It means the stress that will occur on the copper, it is stress tensile as a result of what? Of the force that it is being applied on that material, and it is what? It is tensile. The stress that will experience by steel, it is the stress tensile. That means under the axial load, the stress that we have, or the stresses that we are going to have here, it is the stress tensile. Okay. Now let's go ahead and determine. The stresses under the axial load. Let's go ahead and determine the stresses under the axial load. Now, we know that change in copper equals to change in steel. We know that the formula of calculating the change is FL over AE. Okay. Now, what do we have here? What do we have here? What do we have? Force over area, it is your stress. Now, it means here we are having, as a result of that formula, we are having stress steel, L steel over E steel. What is it that we know? We know that L copper equals to L steel. That's what we know. Then we know that under parallel connection, we are having force total equals to force copper plus force steel. But now, stress equals to force over area. If we're to make the force the subject of the formula, it will be stress multiplied by area. Now, it will depend with the given information. In this case, I will be using the stresses because I'm not given the forces. Now, I'm opting to use what? The stresses. You can use the forces. There's nothing wrong. You will still get the same and the correct answer if you want to calculate the forces. But in this case, I want to calculate what? The stresses. Okay. It means here I'm having stress steel L steel over Young modular steel equals to stress copper L copper over Young modulus copper. L and L will cancel out, then I will make stress steel the subject of the formula. It will be stress copper multiplied by E steel over Young modulus copper. Do I have the values of your Young modulus? Yes, I do have. It is 200 gigapascal multiplied by stress steel over 100 gigapascal. The giga and the giga will cancel out. The 0 and the 0 will cancel out. Then I am left with 2 stress copper. Stress steel equals to, then I will make this equation 1. Let's wipe here on this side. I will make that equation 1. Okay. Then I have force total, which is given, it is 50 equals to stress steel area steel plus stress copper area copper. Do we have the values of areas? Yes, we do have. I'm given 50 times 10 to the power 3 equals to area 1,257 times 10 to the power negative 3 area steel plus the area for copper. I do have, we did calculate it. We got 4,909 times 10 to the power negative 4, right, multiplied by stress copper. That's what we have. But we know that where there's stress steel, we can substitute it with 2 times stress copper. Now I'm having 50 times 10 to the power 3 equals to 1,257 times 10 to the power negative 3. Where the steel, it would be multiplied by 2 times copper, 2 times stress copper plus 4,909 times 10 to the power negative 4. Now, this would be equation number 2, okay? That formula would be equation number 2. Now, I can then solve stress copper. On this side, when I multiply and add, I get my stress as, I'm having 50 times 10 to the power 3 equals to 3,005 times 10 to the power negative 3 stress copper. Then, therefore, my stress copper would be 50 times 10 to the power 3 divided by 3,005 times 10 to the power negative 3. Then I get my stress copper as 16,693 megapascal. Then I can say substitute this answer into first equation. Substitute this answer into first equation. First equation, it is stress steel equals to 2 times stress copper, it is 16,693 megapascal. Then my answer here would be 33,279 megapascal. I've then managed to calculate the stress steel and the stress copper. I've managed to calculate these two. Okay. I've managed to calculate the stress copper as a result of the force applied. Remember I said, as I've explained, that means the stress here, it is tensile. The stress here, it is what? It is tensile, as I've explained. Now, in calculating the resultant stresses, I will use this page to calculate the resultant stresses. Firstly, that's why. In calculating the resultant stresses, it will be stress resultant of steel and stress resultant of copper equals to. Now, of steel here, I got 22,867, and we said it is tensile. It is 22,863 plus, remember it is tensile. Then I go to this one, the stress here, we said it is tensile. That means I will add the 2. It will be plus 33,279. Then I get my answer as 22,863 plus 33,275. I get my answer as, my stress here is 56,138 megapascal tensile. The resultant, it doesn't matter because we've already determined that this is tensile, they are of the same direction. Then coming to the stress copper, We said it that the stress copper here, it is 58,549. It is compression, okay? It is plus. It is compression, it is plus. Then we checked here, we determined that this is tensile. The stress under the axial load, it is tensile. Then it will be minus, okay? It will be minus the determined stress there. It is 16,639. That's a minus. Tensile minus compression plus. Then we get our answer as 58,549 minus 16,639. Then I get my stress, my resultant stress here as 41,91 megapascal. This is how you determine the resultant stresses. Let's see if the answers that we got, they are the same now. Let's see. Somewhere in our calculation, we did get this. We said it that it is tensile. Let's see if we can prove that. Under the 22, where's our 22? There it is. We said it is tensile. There it is. Can you see that? Then we did determine the 58. We said it is compressive. Where's the 58? Where's the 58? Let's go to where we've made the calculations. Where's the 58? There it is. Here's the 58. There it is, the 58. We said it is what? Compression. Can you see that? Then we said the 33, 20, it is tensile. Now let's look for that. 33, where's our 33? There it is. There it is. We did indicate that this is tensile. Can you see that? There it is. We said it. It is tensile. Can you see that? Tensile. Then we got the 16. The 16, we said it is tensile. Let's see the 16. Where's the 16? There it is. It's a minus. We said it. It's a tensile. This is a compression. It's a tensile. It's a minus. Let's look for the 16. There it is, the 16. We said it. It is tensile. Then let's check the resultant. There it is. We have 56. Then we've got 41.9. Let's see. We've got the 56. We've got the 41.9. There. That's how you calculate. This is how you work out this equation and the resultant stresses. I hope this will help you and it makes sense. Thank you, good people. If you've got any question, leave a comment, leave your question on the post, like, comment, subscribe on this video. Thank you, good people.